Without further ado, our first speaker today, who's much better dressed than I, he's a legend, Eric Barton.
Gosh, what an introduction. Where's the little button that goes ping? I mean, oh, that one, yes. Excellent.
It doesn't ping, sadly.
It doesn't, sadly. Well, you liked the Monty Python reference there.
I loved it.
Hello, I'm here today to talk about Exascale. And I guess it's my personal view that Lustre will have a big part to play in Exascale. Mostly because there's such a lot to do and you've got to start with what you have. So first of all, I want to talk about what I believe are the main issues that Exascale I/O has to address. Really, it's a combination of what the technology can deliver, what the application programmers want, and we have to come to some sort of fusion of all of those things and deliver a storage system that actually works. And so at the end of the presentation, I'll talk a little bit about an idea for an Exascale file system that we're working on, and see how you like that. Okay, I think it's worth actually calling out some actual numbers that describe the way the technology is going. So those numbers, the today numbers, are sort of current best guesses for what's actually being developed right now. Some of them may be a little bit aggressive, but for 2020 you can see that there's an explosion in some of the dimensions that we have to work in. So for example, the total number of nodes in the Exascale file system may go up by a factor of 10 or so, but the number of threads per node is going up by a factor of 100. That's take the two together, and now you have total concurrency that's 1,000 times more than we have today. That's kind of saying that individual threads in 2020 are going to be computing at about the same rate as individual threads today, but there's just going to be 1,000 more of them, 1,000 times more of them. Memory size is going up, and that's forcing the file system size up as well. And the need for defensive I/O, that's one of, a major driver, obviously, in Exascale systems, because as the system gets larger and larger, the total reliability goes down and down. And file systems today have been designed to fail, or to cope with failures, but file systems in 2020 don't have to just cope with failures, they have to live constantly with failures. And so if there are significant pauses while a failure occurs, it's going to totally hose the throughput of the whole machine. So continuing today's bulk synchronous checkpointing model, where basically you are snapshotting the current state of the application periodically so that you can restore from that snapshot and keep on going. Given the reduction in time that you expect between, that you'll actually get to run uninterrupted, then although the memory is getting bigger and bigger, the requirement is to achieve defensive I/O in a shorter and shorter period. And so, if you like, the performance requirement, certainly the bandwidth requirement on the file system is increasing relatively quadratically under these two different pressures, which is a tall order. So, file systems today, we're aiming to peak at the hero numbers are aiming to be in the 1 to 2 terabytes per second range. In 2020, the requirement is for on the order of 200 terabytes per second reliably delivered to applications. Not only that, but the applications are going to have much more complex models than today. The models are going to be spread out in memory, and so you've got all this scatter-gather I/O that's going to try and make it into persistent storage at 200 terabytes per second. That's a tall order. So the thought is really that if we can peak and reliably deliver peak bandwidth at that rate to catch these defensive checkpoints, the defensive I/Os, then we can then drain the buffer that caught that at a relatively conservative 20 terabytes per second, which is only an order of magnitude on today's bandwidths. So it's nice to have easier challenges. Coupled with that is the object create rates, which today, 100,000 object creates per second is doing incredibly well, actually, on today's file systems. To turn that, to let that match the concurrency, if you like, explosion that we expect of a factor of 1,000, then we're going to need to be able to support object create rates of 100 million per second. Again, that's a really tall order. So, from the applications point of view, why is this happening? Well, simulation models are getting bigger and bigger. Not only that, but they're getting more complex. They're able to adapt more to real world situations. They're able to model real world simulations much more finely. You tend to have not just a single simulation model, but many simulation models that all have to work together. Uncertainty qualification means for some classes of applications that you're no longer satisfied with having one simulation run. We have to have 1,000 simulation runs with initial conditions all perturbed. And so there's a huge amount of data getting generated here. And in order to make sense of it, there's huge amounts of application metadata that is annotating it, labeling it, letting you know what the data all means. And so what the application programmers are after is more of an object database than an I/O system. So today we think in terms of files and reading and writing. And I think a better model for these hugely complex applications is one in which we think of objects which we instantiate and persist. So we pull them in from permanent storage, we analyze, we augment them, we persist the results of the simulation. So with all of this object data, there's a massive requirement to be able to organize it efficiently, and no longer at human scale, but at massive exascale. The picture on the right, actually, I first saw in one of Galen's presentations, and I think it really captures the idea. Today we have, well, the manual system files in manual filing cabinets, and really in exascale we're going to have endless ranks of data disappearing off into the distance, and we need to have automatic ways of crawling over it and finding out the information that we want. Where's my 100-year wave, for example? If I've been simulating oceans, there's a massive amount of data there. Somewhere in my 100 years of wave simulations, I want to know where is the tsunami going to happen. The other issue that we have to address then is storage management. Even though we've got huge quantities of data within models, at a gross level we still want to be able to move these models around between different storage tiers, so migrate them off to the long-term archive. or bring them in closer to the machine for analysis. So this is a guess. It's a current best guess at what an exascale machine might actually look like. So the grey boxes represent the compute nodes. You know, all 100,000, maybe even getting on for 1 million of them. And they'll be connected together with some network. And due to the sheer size, the sheer numbers of nodes, it's most likely that that network is going to be some sort of a torus, one in which the ratio between networking and compute is constant. Anything else is really too expensive to build at that scale. Now these networks, if you use them well, if you use them scalably, it's possible to do scalable computation on them. If you don't use them well, they'll congest internally, and therefore you have to be very careful with how you use the internal network of the exascale machine. If you expect to be able to use it for I/O staging, for example, you may have to think hard about that. So it's likely that the I/O nodes will be off to one side, because if I/O communications are using up the network while the application is attempting to use the network, there's going to be a conflict. And unless you're going to implement some sort of quality of service and basically reserve less than 100% for the applications, which is something that applications programmers never like to see, then you're going to have to accept that I/O needs to get out of the way as soon as possible and stay away from the application communications. So it seems likely that I/O nodes with some sort of NVRAM that can drink the fire, well, not just one fire hose, but the thousands of fire hoses that the exascale machine will be spewing out. It's likely that they will be sort of edge of the mesh style nodes. Now, it remains to be seen whether we want to give those I/O nodes their own network. If you think that we have a fan out probably of maybe 100 to 1, so that each I/O node is only dealing with 100 compute nodes, then the I/O portion of the machine is only 1% of the whole machine size. Now, for on the order of, say, 1,000 I/O nodes, we can afford a network that has better properties for non-local communication, and therefore we could think of maybe a fat tree spanning those nodes. That's something that remains to be seen. But something that seems pretty definite is that the I/O nodes will have some sort of NVRAM on board. And the reason being that the performance that we need, the level of bandwidth that we can get, and the granularity of I/Os that we need to capture from the exascale machine are so fine that we're going to need something that's way better than disk, not just at bandwidth, but also at IOPS. The cost of that storage, however, is going to be prohibitive if we try and make all of the storage like that. So what we kind of end up with is this concept called a burst buffer, which I'm sure many of you are familiar with, in which the NVRAM on the edge of the machine is able to take the peak bandwidth and message rates that are required, and then, if you like, impedance match the I/O requirements of the applications running on the compute nodes to the capabilities of the disk-based storage system, which will be there for capacity. It's also likely that the disk-based storage system, and if you look at systems like Spider, Oak Ridge, it's like one of the first systems that sort of showed this approach was feasible. That we have some sort of site-wide storage network. In 2020, it's probably some sort of evolution of InfiniBand. That's the network that's going to be constantly running at 20 terabytes per second, draining burst buffers and filling and pre-staging data into them. So back on the shared storage system, we've got probably the same number of server nodes as we had I/O nodes on the edge of the Exascale machine. That will almost certainly need its own quite capable network, because we'd like to use those storage servers not just for capturing the 20 terabytes per second stream from the Exascale machine, but also for doing some sort of indexing and searching, pre-filtering on the local storage. It's likely that those nodes will also have NVRAM, because the file system has to remember not only large streamy stuff, if you like, it also has to manage and store small tiny stuff. And the small tiny stuff is probably file system metadata and application metadata. And actually the vast majority is probably application metadata. So concurrency is the big issue. Death by 1,000 million cuts. So what do I mean by that? Well, I've got these mesh elements in the compute node memory, and the mesh elements might be as small as half a K, or they might be, a few megabytes. It depends on the class of application. But if you look at the message rates that future networks are likely to support, which is going to be on the order of hundreds of millions per second, and the bandwidth that they support, which is going to be on the order of hundreds of gigabytes per second, then really you can't go much smaller than a couple of K before the message rates are going to dominate the performance. So provided you keep your mesh elements in contiguous storage, we're kind of saying actually you can afford to push your objects out into the network at full bandwidth. And you have to catch those objects on the I/O nodes at the same sort of bandwidth. Now, not only do you have to catch them into memory, you have to then push them into the NVRAM on the I/O nodes. And so it's likely, well, in fact, it's definite that you're not going to be able to involve any sort of operating system in that part of the flow. So on the compute nodes, you'd expect to see some sort of stripped down runtime. On the I/O nodes, we're expecting to see Linux, but the processes which are helping perform I/O staging, if they make any sort of system calls in the critical path, then you've totally hosed your throughput. And so really the burst buffer and the networking both need some sort of OS bypass at that point. The other thing that's quite a thing to consider, and certainly in the early stages of Lustre, it was an issue that was kind of ignored, but multi-core is here to stay, and unless the I/O staging is designed from the ground up to exploit multi-core, multi-socket nodes, then once again you're not going to be able to support the throughput rates required, because you really have to have laminar data flow all the way from the application to the burst buffer. As soon as you get data sort of converging, forming turbulence, the throughput just totally falls off. And so applications actually are probably going to have to abandon the bulk synchronous model themselves. Barriers across 1 million threads, 1 billion threads, the jitter issue becomes, totally dominates. So new models of processing in which individual threads proceed totally asynchronously, and it's coupled with a new model of defensive I/O in which small parts of the model are committed into the permanent storage. What that means is that if the file system does any sort of locking in order to provide the persistence and integrity guarantees that it has to provide, then once again we're going to be interfering with the flow of data. And so we have to expect massively asynchronous I/O, and the file system has to be as asynchronous as applications demand of them. Ooh, I better speed up. Okay, so huge amounts of metadata, and the metadata and the data it references have to be consistent with each other, because metadata at one level is data at the level below. So if you look at an HDF5 file, for example, Lustre today hasn't a clue what's in there. It just, it's just binary data. But the HDF library considers it to be large amounts of metadata plus leaf data. Excuse me. And if we don't provide some consistency guarantees and integrity guarantees in the low-level file system to the upper layers, then it's going to be impossible to implement. So, we're going to have some sort of end-to-end guarantees that the object I persisted makes it all the way to permanent storage, and when I reinstantiate it, actually I get the same object back. Not only the same object, but all its relationships to all the other objects they are all intact. So that really means some sort of transaction system. But once again, it cannot be a synchronous transaction system, because as soon as we make things synchronous, then the flow will stop. So we really need to look at where do we need strong transactional guarantees, and where can we relax a little. So for example, if a failure causes some free space in the file system to be lost, that's the sort of thing that we can leave in the filing system for a scrubber to clean up. The scrubber, the namespace or the object space in the file system is going to be many, many, many billions of entities. And so you can't really expect the scrubber to get round to looking at everything with a period of shorter than weeks, probably. If you depend on it getting around the whole system in hours, then probably you've used up all of your bandwidth just on checking the file system. So scrubbing is useful for these sorts of long-term repairs, and probably something that we want anyway, just to ensure that bit rot isn't causing all of our integrity information to become too far out of date. But everything else, all other failures, we have to implement cleanups that happen in pretty short order, so that the file system and the application data and the application metadata all remain consistent with integrity. So, global storage, the shared file system, local storage, the burst buffer. What's the local storage really going to look like? Is it going to look like a file system? Is it going to have a namespace that somehow shadows the main file system namespace? Is it going to be strongly coherent with the global storage, like a cache, or loosely coherent, just used in the workflow? I think one of the major issues you have to look at here is fault domains, and ensuring that we don't link fault domains together unnecessarily. So for example, if you have storage in two separate tiers, but you have to, but your consistency guarantees require that the nodes in those two different tiers have to communicate with each other very, very frequently, then effectively you've doubled the size of your fault domain. A fault in any one of those nodes is now going to make all of the nodes have to somehow take part in recovery. So it's important to be aware of that when you're designing the file system. So I'm running short of time. So one thing, I'm just going to something very close to my heart really is that not only does this file system have to be demonstrated as a prototype, it's actually got to run in production. And that means that the stabilization effort required in order to turn a research file system into a production file system is non-trivial. And therefore the research has to be starting today and the stabilization effort has to be starting tomorrow. And so in order to be able to just develop everything that we need in time, we really have to build on existing components when possible. But some subsystems are going to be required brand new, a total rethink. And the major issue is that all layers of the I/O stack work together properly. So filing systems engineers like to bitch about middleware developers and say they don't know how to drive the system properly, and I guess middleware developers bitch about applications programmers saying they don't know how to use the middleware properly, and that's got to stop. And everybody's got to understand the whole stack, you know, from the hardware right down at the bottom all the way up to the applications right at the end, which is why I think programs like Fast Forward with their co-design requirements are just absolutely the right way to go at it. So the idea that we're pushing at the moment is this thing called DEOS, which is basically the concept that the file system namespace should be there to work at human scale, so that people remember where they put their stuff. You can have your POSIX files, your home directories maybe. Everything, you know, thousands of entities that individuals can remember. The millions and billions of entities that are going to be in these exascale simulation models, you definitely need some sort of an object, system, naming system that lets you organize these together. But exposing them to the namespace you use for storage management seems like the wrong way to go. And therefore, this concept called distributed application object storage. The idea of that is that you make containers there. In the namespace, they appear like regular files, but internally, they have some sort of, to be determined by applications and middleware, object namespace. So you could imagine, for example, that we could make a MapReduce container, which looked rather like HDFS, and actually you could run Hadoop on. Or you could have an exascale simulation container which had a global climate model in it. And you can coexist with your POSIX Stripe files just like we have on Lustre today. So we'd like to develop this DEOS model based on Lustre. The DNE project in OpenSFS is our first toe in the water in sharded indexes, which we're using for parallel directories. I think that technology can be taken further, and so we can create a scalable sharded object container within the existing framework that we have in Lustre. But then the middleware and applications that we grow on top of that, that's where some real innovation has to occur. So I think I have run out of time now, so if there are any quick questions. Corey?
Hi. You spent a lot of time talking about the defensive I/O checkpoints,
yep.
I/O for exascale. Are you not concerned at all about normal legacy scaling up regular apps into exascale?
I don't think legacy apps are going to scale into exascale, full stop. I think they will run on tiny portions of the machine, but as soon as you start spreading them as thinly as you need to in order to exploit the whole machine, then they'll start getting efficiencies, in the thousandths of a %. So I think fundamentally, part of the whole DOE Exascale program is researching new application programming concepts, and that's a big part of this. And the I/O system has to be developed totally in conjunction with that, so that we don't end up once again with this, we built you the perfect, the perfect, POSIX we can't rebuild POSIX and say here's the model, go and use it, because we actually have to, the applications and middleware engineers, developers really have to understand what is it you can and can't do in a storage system, and what are the latency constraints and the integrity and transactionality constraints. And so we have to push back on applications a bit, and applications similarly have to push back on us and do those things together. So yeah, I think the legacy, yes, of course we will want to be able to support legacy, but it's not going to get the efficiency that you'd like.
Thank you, Eric.